Hey Alex.
Hey Billy.
Have you done the hydro homework yet?
Yeah, I actually have. It was pretty easy for me.
I was looking at problem 5.60 and I was having trouble. I was wondering if you could help me.
Oh, most definitely. It's really helpful. I happen to have the entire solution here on this blackboard.
Great.
Well, here's the problem we have. Here's the inflow air, which is 1d velocities. Well, it's 1d flow, so it's coming in as a uniform to velocity. Then there's going to be a mesh here that is going to be resisting that 1d flow. And then it's going to result in a non-uniform flow that is dependent on the radius, as you can see. It's important that we put our axis here, with the x being directly in line with the middle, and the y we don't really care about because all the flow is just in the x direction. So the givens that were given to us were the pressure, the velocity 1, and then the pressure 2, the density of air, and then the diameter. We're going to keep everything in pounds per feet squared just because it's going to end up being easier for us. As you can see here, the givens, make sure that you get the density of air from the front of the book. And it's going to be in slugs per feet cubed, which is good for us because in the end, it's going to cancel out the feet per squared and the second squared, so it all works out for us well. Like all of our homework problems, we should really kind of start by listing our forces and listing our fluxes. So to begin, we have our forces. There's going to be the pressure 1 times the area 1 that's coming into the system. Then there's going to be a negative pressure 2, area 2, or times area 2, because that's going to be going backwards onto our control volume that we're going to have. And then we have the negative dx, which I said is the mesh that's going to be resisting the airflow. The fluxes that we have, there's going to be obviously an influx and an outflux. For our control surface 1, as I said, it was a 1D flow, uniform. So all we have to worry about is we can skip kind of the integration part and we can just go to the fact that the equation is density of the air times the velocity coming in times the inflow. Make sure that's a negative inflow because, like I said, it's coming in, so it's negative Q. And that just comes out to be negative density of the air times velocity squared times area. The control surface 2, that's where it gets a bit more tricky, and that's where the real hard part of the problem comes in. So the equation is, though, for control surfaces, the integral of the density times the velocity crossed with the velocity dotted with the normal, dA. Fortunately for us, like I said, everything's in the x direction. So the velocity 2 dotted with the normal is just going to end up being the velocity 2. So then we can skip right here and write, well, the density comes out of the integral, and then it's the density integral v2 squared dA. So this would be pretty easy, but it's just that since it's not uniform at all, we need to somehow relate the change in height or the change in radius with the velocity. This is where these important kind of equations come in. So the velocity 2 equals v max, little r, big R. Big R is going to be a constant here. We're going to say it's 1 foot just because we're keeping everything in foot. And then this radius right here is going to be the one that's changing and the one that we're going to really integrate. So if the little r ends up being 1 foot, then the v2 will be v max, and just like if little r is 0.5 foot, the v2 is actually going to be half of the v max. And something you should probably have remembered from calculus 3 is kind of integrating it, and when you're doing radial integration, you take the a equals pi r squared, then derive it, and it becomes dA equals 2 pi r dr. So we can take this, plug it in here, we can take this, plug it in here, and we end up getting the density of air is the integral of v max squared, little r squared, big R squared, times 2 pi r dr. And integrate that out, you end up getting 2 pi density of air, v max squared, over 4, times little r 4. The big R is obviously out because we're keeping it in feet. It's only 1, so 1 squared, still 1, and that goes out. And simplified equals the pi density air, v max squared over 2. And to be honest, I actually needed a little help on the rest of this problem. So I'm going to turn it over to Nathan here to really help me out.
Okay, yeah. So at this point we still have 2 unknowns. We don't know what Vmax is, and we don't know what the drag force from the mesh is. So to find Vmax, we have to use the conservation of mass principles. Looking at the rate of change in the mass at control surface 1, we know that it's negative rho v1 a1. It's an inflow, which is why it's negative. And then the rate of change of mass at the control surface 2 is going to be defined as the integral of rho times the dot product of v2 and n2 times dA. plugging in kind of how we've been defining all the variables all along, we're just going to use this equation and say that, so the integral from 0 to big R times the density times Vmax little r over big R, which is V2, times 2 pi r dr, which is dA. We're able to integrate that equation to solve for the rate of change of mass at the control surface 2, and that would give us 2 pi rho times the integral 0 to r Vmax over big R times r squared dr. And this gives us this equation here. R is 1, so we're able to know that the rate of change in mass at control surface 2 is 2 pi rho times Vmax times r squared over 3, and r squared is really just 1, so we can just go take that away. And then the whole principle of conservation of mass says that the mass in this problem is not changing. So for the net flow, so the sum of the changes in mass is 0. So we just sum the m dot 1 and the m dot 2, and we're able to derive this equation. And what that is negative rho v1 times a1 plus 2 pi rho Vmax r squared, which is 1 over 3. And when we understand that a1 is pi times 1 squared, so a1 is pi and v1 is 100 feet per second, which are both given in the problem, we're able to simplify this whole thing and find the only unknown, which is Vmax, and that is 150 feet per second. And then we take all that information and putting it into a conservation of linear momentum system. We know that from the forces that we had that we talked about at the beginning of the problem, we have P1A1 minus P2A2 minus dx, which is the variable that we're solving for, is equal to the flux, the sum of the fluxes, which is negative rho v1 squared a1 plus pi rho Vmax squared over 2. And if you look at this problem, you'll see that we've solved for everything except for dx. So we just plug in everything we know. So this is 28.8 pi minus 21.6 pi minus dx is equal to negative 1 times the density of air times 100 squared times pi plus pi times the density of air times 150 squared times 1/2, which is from that. And solving for that, you are able to arrive at the conclusion that dx is 13.3 pounds.
Great, thanks.